And so let's take a look at some of the types of optics that are available. Again, as I mentioned, light microscopes are generally built on a stand, and the stand is the basic element that contains the focus knobs, of course, and it has racks for the stage, for the condenser. It has the built-in illuminator. It's got the binocular eyepiece tube, a place for that. And there also are places for substituting different condensers for different types of objective lenses, even for different kinds of eyepiece tubes, and so on. You can buy optics packages when you buy a light microscope. It doesn't have to be strictly bright field. You can include, the cheapest, probably best value in terms of a specialized optics package would be dark field. And it's very rarely available. I'm surprised that more people don't use it. I'll explain the principle in a little while, but in dark field, you can get the much better resolution than you can get in bright field or in phase contrast, a tremendous increase in resolution, and there isn't anything, living or dead, that you cannot see in a dark field microscope. Not a single thing. You can see bacteria at a magnification of as little as 40 power. You can see them swimming, the smallest ones, as a matter of fact, and they would be completely invisible in bright field. More commonly, you'll find phase contrast optics. Phase packages are kind of expensive. A basic student model bright field microscope of good quality will run you maybe $800, $1,000. A phase package might add about $1,200 to it, or more, depending on the brand and the numbers of bells and whistles on the darn thing. There's another feature that I'll just mention in passing, and it's called differential interference contrast, or Nomarski, or sometimes Hoffman modulation contrast. It's a method that works with polarized light to produce what looks like almost a three-dimensional image, a raised image. It's very good for looking at colorless objects where you want to see structures and shapes and so on, such as an amoeba, or even bacteria, depending on what sort of information you want to acquire. DIC optics are very expensive. There is a little trick to getting it on a light microscope, the bright field microscope. If you have a condenser that can be placed off-axis, just very slightly, you can mimic DIC very readily, and it doesn't cost you a penny. So I've talked about bright field microscopy, talked about dark field, I talked about phase contrast. All of these different kinds of optics involve different methods of producing contrast between a specimen and the field of view. If there's no specimen at all in your microscope, what you see is a background, usually a uniform background, and nothing in it. If you have a specimen that has no contrast at all, you still see nothing but background with nothing in it, even though there's something in the light path. There has to be some principle by which the specimen modifies the light as the light goes through it, around it, bounces off it, or whatever. In bright field microscopy, the object itself has to absorb light somehow. Usually we stain an object, we view a pigmented object. It might be thick enough that it absorbs some light just by virtue of its being a thick specimen. What we then see is a specimen with pigmentation or maybe various grays or browns against a bright background, and hence we call it bright field. In the bright field microscope, the light comes up into the condenser. It comes up through the stage into the specimen. It's transmitted through the specimen, which then absorbs some of the light, producing a contrast. And from there, the light from the specimen enters the objective lens into the aperture. It's magnified. The magnified image is projected upon the back of the objective lens. And then the light follows a path, sometimes through a prism, as in the case of this binocular microscope, into the eyepieces. The eyepieces, in turn, magnify the image some set amount, usually tenfold, and we see a nice high-resolution image. Dark field optics are probably the best package you can get for the value, and unfortunately they're often not available. In dark field microscopy, an occulting disc, an actual opaque disc, is placed in the microscope light path just below the condenser lens. The only light that can strike the specimen has to come from the side at an angle. And what happens then is the light comes up, strikes the specimen. If it misses anything and it goes straight through, such as straight through the medium, water maybe, or just glass, it misses the objective lens completely, and all we see is dark. If there's something in the path, any kind of particle, a particle of dust, bacterial cell, parts of an amoeba, contractile vacuoles, cilia, flagella, the light is scattered. It actually reflects. And that reflected light will change direction and come up into your objective lens. Now you might be thinking, wow, we're looking at reflected light. It probably takes a lot more light in order to see anything at all, and you'd be right about that. Usually we have to turn up the illuminator to maximum, and we have to have very, very good optical systems. That might be one drawback to using bright field, or dark field rather. But it's extremely effective. If you view, let's say, a pond water sample with some nice debris in it, algae and rotifers and bacteria and so on, in bright field, you might see a little bit of movement. In dark field, it is absolutely teeming. It's a jungle in there. It's a wonderful mode of optics, and the resolution is incredible. If you go to 400 power with dark field, you can see not only bacterial cells and see their shape, you can see spores, you can see even the outline of the cell wall. The resolution is incredible. It not only approaches the theoretical resolution of a bright field microscope, but probably exceeds it. Phase contrast doesn't do anything for resolution. It's about the same as a bright field microscope. But the principle of phase contrast allows you to see colorless objects based on their ability to refract light rather than on any dependence on color or staining or even thickness. So something such as an amoeba, which is completely colorless and is very, very thin when spread out on a slide surface, doesn't absorb much light at all. In bright field, it looks like maybe an outline at best. You can see one if you crank up the contrast very high, and then you distort the image. Phase contrast, on the other hand, gives you a pretty decent resolution, but tremendous contrast. Where the contractile vacuole of the amoeba, for example, was a bare outline, it becomes a nice gray patch, and the nuclei show up, the food particles, and so on. With phase contrast, you can even see the differences between the plasma sol and the plasma gel of an amoeba pseudopodium, something you really aren't going to pick up at all in bright field. Now, phase contrast optics are kind of expensive. They require modifications to both the condenser and specialized objective lenses. There are elements in the lenses that affect the passage of light, and there are annular rings that have to go into the condenser. You have to have a different type of annular ring for each magnification of objective lens, and thus the packages cost, as I mentioned, upwards of a few $100s to $1,000 or so. The principle is to put again, we have a disc in the center blocking light coming directly to the specimen. Then there's a ring of light that comes around the disc, and then it's blocked again. So instead of a column of light coming up to the specimen, we have a cone of light that comes up to the specimen. And when light strikes the specimen, if it strikes a portion of the sample that has a very high refractive index, the light is scattered all over the place. If it strikes a portion that has a very low refractive index, a contractile vacuole, for example, that's all water, or maybe the medium around an amoeba or whatever your object is, then it's not scattered very much at all. Now, the light that tends to be scattered toward the center of the light path, as a matter of fact, enters a portion, an element in the objective lens that retards the passage of light a little bit, about a quarter of a wavelength. In addition, light that's scattered itself through an area of high refractive index slows as it passes through that portion. Remember, way back I mentioned that that light, when it enters a medium with fairly high refractive index, slows down. If you slow light by a half a wavelength, it becomes out of phase, 180 degrees out of phase, with light that comes straight through. And so in the objective lens, when the light that is scattered is recombined with light that isn't scattered from the same area, you get interference and you get a dark spot. On the other hand, if the light, when recombined, is in phase, you get a bright area. What we do is adjust the position of the annular ring and the objective lens, line them up such that we get the maximum dynamic range. Just as you do in old black and white photography. We want the blacks to be as black as we can get them. We want the brights to be as bright as we can get them. In phase contrast, it's shades of gray. But nevertheless, with just the right alignment, which doesn't take very much effort at all, we can get some beautiful contrast on an object that looks like nothing in bright field. It just disappears. You can see cilia, you can see flagella, you can see nuclei, contractile vacuoles, food particles, cytoplasmic granules, all sorts of wonderful things. I'll spend just a very short time on differential interference contrast. It operates on polarized light. This method of enhancing contrast also operates on the principle that any object has variation in refractive index among its parts. What we do with differential interference contrast is polarize the light coming up to the specimen, and polarize light from going through a couple of different filters follows two slightly offset paths, so that when it's recombined, we get slightly offset images, which give us a three-dimensional view. The filters, the polarizers, and the whole optical package for DIC or Nomarski